Thanks very much. I'd like to introduce my co-workers, my colleagues at Greenwich, Dr. Wang and Dr. Jia, who unfortunately can't be at the conference today. I'm going to talk about the fire and evacuation simulations of a fatal fire in 1985 at Manchester Airport on Boeing 737 aircraft. This is a very special fire for me. It's quite an emotional fire for me. It's what started my fire career. It started me doing fire modelling and evacuation modelling. It led me to develop the Smart Fire CFD Fire software and the Exodus evacuation software. It was the first time I came into contact with dead bodies. It was the first time I came into contact with survivors from quite a horrific fire incident. And it's the first time I came into contact with families of the bereaved. So it's quite an emotional topic for me. And as I say, it started my career in fire research. I'm going to give you some brief background into the fire. The fire incident occurred on the 22nd of August 1985 at Manchester Airport. It was a result of an uncontrolled combustor can fire in an engine during the takeoff taxi. The external fuel fire, the combustor can burst and it ruptured fuel lines and started an external fire. The external fire entered the cabin through a burn-through of the fuselage, and the external fire, while it was controlled to a certain extent by the firefighters, the internal fire was not controlled in the slightest, and so it spread through the interior of the cabin quite rapidly. 2 of the 4 cabin crew perished in the fire, and 53 of the 131 passengers died as a result of this fire. 15 passengers were also severely injured and later succumbed, 2 of them later succumbed to their injuries after some time, after some number of years after the fire. Okay, so you can see the fire here, starting on the port engine side here. Smoke, the wind is blowing in this direction, blows the smoke over the fuselage, obscuring the aft exit. And that's quite an important point which we'll come to in a little while. The aircraft is a 737, Boeing 737 aircraft. It has 3 pairs of exits, 2 in the front, 2 over the wing and 2 in the aft. The overwing exits, as you know, are type 3. They're small exits, they're hatch exits you have to climb through. And in the actual incident, the white seats are where passengers perished. The blue seats show you the people went through the blue exit, the green through the green, and the red through the red. 35 people used the right one exit, 17 people used this left exit, and 27 used this exit. The R2 exit was opened by a cabin attendant, but because the smoke was blowing over the fuselage in this area, no one actually used that exit, and in fact smoke entered the cabin through, some smoke entered the cabin through this open rear exit. Again, that's an important point which I want to come back to a bit later on. Now, there were a number of problems with this in this particular incident. The right one exit got jammed. The exit actually malfunctioned. And to the credit of the cabin crew at the front, he didn't panic or he didn't spend too much time trying to open that jammed exit. He came over to the L1 exit and got that opened in 25 seconds. He then went back to the R1 exit and eventually got that open after 70 seconds. This is quite important. The overwing exit is operated by a passenger, and it normally takes 12 seconds for a passenger to open that exit. The passenger at that exit didn't know what they were doing. They couldn't get the exit open, and somebody else had to lean over and get that exit open, and that was opened after 45 seconds. The front exits and the rear exits are normally opened in 8.2 seconds in certification drills, and that's what we expect the crew to be able to get them open in a real incident. And the overwing exit, on average, is opened in about 12 seconds in certification drills, and that's what we expect passengers to be able to do in a real incident. But you can see the delays in opening all these exits. Now, the research questions we've got in this particular fire is, could the loss of life have been significantly reduced if the R1 exit had not malfunctioned? We also would like to know, did the delay in opening the right overwing exit have an impact on survivability? And did the opening of the unused R2 exit in the rear of the aircraft contribute to the high loss of life in this particular incident? and there was a lot of speculation in the press that the cabin crew member at the rear who opened that actually made the situation a lot worse. That cabin crew member actually perished in the fire. She stayed there defending the exit, making sure passengers didn't go out in that fire, out of that particular exit. So we want to know, did opening that exit actually contribute to the high loss of life in this particular incident? So what we're going to use is the smart fire software to simulate, the CFD software to simulate this fire, and we're going to use the air exodus software to simulate the evacuation. We couple the two, and we bring the two together, and we transform the fire data into the evacuation simulation software, and we look at the impact of the heat, the smoke, the toxic gases on the survivability of the passengers. This is the first software that was able to do this, linking of fire and evacuation together in this detailed CFD analysis and detailed evacuation analysis. And again, as I say, the motivation that I had for doing this was to try and understand this fire and understand why so many people perished in this fire. I'm not going to go into the details in this. You can see some of this in the paper. Basically, we in the CFD model of the aircraft fuselage, we split this up into a number of zones, and we average the CFD data for the temperatures, the smoke concentration, the toxic gas values, and so on, and transfer it into the evacuation model, into these zones, these averaged values, and then the agents that are moving around react to the toxic hazards using fractional effective dose models and behavior and smoke models, and so on. The average values are at two heights, at head height and at knee height. Why do we have it at knee height? Because in these sorts of fires, the conditions at head height become so severe that people have to crawl to get through to an exit. So we have the toxic hazards and the heat hazards at both heights. Now, I want to talk very briefly about the fire simulation. This is quite important. We actually went through a two-phase approach to do the fire modelling. In the first phase, we tried to reproduce the incident fire and evacuation environment in order to demonstrate the validity of the modelling approach. Okay, so in the first step, we try and recreate, it's a forensic reconstruction of this incident to see if we can match what happened in the real incident. And then in the second phase, we then use these, if you like, validated model to explore what-if questions. And the what-if questions we're going to explore are those three questions I raised before. But the first phase of this work was actually quite complex because there were a number of factors. There were 6 key factors that we needed to specify the fire model with high degree of reliability that were actually missing, that we didn't have detailed data for. And so some of these things are, for example, the volume and heat release rate of the external fire, the start time and the duration of the cabin burn through. And so, and there were also some evacuation parameters, for example, the passenger response times. We didn't have those values. And so what we did was we did an iterative process in the fire and evacuation modelling where we would make the best educated guesses for the unknown parameters, run the simulations and see how well it matched what actually happened. And when we saw there was a bit of a mismatch, we would change some of the values and go through the process again until we got good agreement. And so there was this 3-step process. We had 11 key fire and evacuation outcomes we could test the model results against. And we went through this iterative loop, surprisingly very few times. We had to go through this route 3 times, and then we finally got a very good agreement with the actual fire and evacuation. The fire simulation, to give you some idea, that's the fuselage. We had 144,000 computational cells in this structure. We used a 1-second time step to march through the CFD calculations. We were calculating heat, smoke, toxic gas, CO, CO2, HCN, and HCl were predicted during the simulation. And we had a spreading fire model. So the fire was actually spreading and combusting the actual materials in the cabin. We then, this is the exodus representation of this particular representation. We used what we call the extreme behavior options in air exodus. When you're doing a certification analysis or a design analysis, you run it in certification mode. And so the passengers don't behave in an extreme way. In other words, they don't climb over seats to try and get out. They don't crawl. They just going into the aisles and trying to get out as quickly as they can without behaving in an extreme way. But when we're doing a forensic analysis, trying to simulate something that really happened, then we turn on these extreme behavior properties of the model. I want to just briefly show you how good the fire simulation was. This is at the end of doing the 3 iterations in this loop. We got pretty good agreement. What I'm going to show you here are some of the differences. This diagram here shows you the damage to the internal seats. These dark seats here are completely burnt out, and these dark seats in our model are completely burnt out. These hatched seats here are severely damaged but not completely burnt out. And in our model, near where the fire entered, we also have completely burnt out seats. So we are overestimating the damage to the seats in the point of the fire assault. Now, so we've overpredicted the damage in this area. Instead of having severely damaged seats, we have completely burnt out seats. The difference is due to the nature of the burn-through. Remember, we don't have exact data for the burn-through. We're having to estimate that. And it's also, probably more significantly, it's due to the firefighter intervention. Because late in the fire, the firefighters are squirting water on this and they're preventing these seats from getting damaged. We're not modelling that part of the fire. However, by the time all the passengers get out of the model, these seats aren't severely damaged. So the fire environment is actually very close to what happened in the actual incident, even though we end up with completely burnt out seats. While the passengers are still inside the aircraft, the damage is appropriate. In this diagram, I'm showing you, again, the actual accident, showing the white seats are where the fatalities are, and this is our prediction for the evacuation. Our white seats also show where the fatalities are. And so, in the accident, most of the fatalities occurred in the rear of the aircraft. That's what we're finding in the simulations, the predictions. We have some survivors in the rear part, in the real incident. We're having some survivors in the rear part in the simulation as well. So we're getting a very good agreement with what was actually happening in the actual incident. So basically, we simulated the fire. After the iterative process, the fire and evacuation, we got very good agreement. There were 55 fatalities. On average, when we run the simulations a number of times, we have 55.6 fatalities. Okay, so we're getting very good agreement. On the basis of that, we looked at the 4 what-if scenarios. And in the 4 what-if scenarios, we're looking at 4 different cases. We open the R1 exit in 10 seconds, the required amount of time. What difference will that make to the outcome of the fire and the evacuation? In scenario 2, the over-wing exit, we're opening in 12 seconds instead of 45. The certification required exit opening time. In the 3rd scenario, one of the most important ones in my opinion, we close the rear exit that the cabin crew member opened, and we see what effect that has on the fire and the evacuation. And in the 4th case, we assume all the exits open in the appropriate time. And what impact would that have on the outcome? Now, when we're changing the exit opening times, we're going to change the fire dynamics inside the fuselage, so we have to re-simulate using the CFD and rerun those models to get the new fire environment. And what I'm showing you here is the temperature versus time, and this is at a location in the front of the aircraft, and here we have the temperature versus time in the middle of the aircraft near the overwing exit. And the key thing to note here is that for all these scenarios, apart from when you close the rear exit, this red curve is for the case where you close the rear exit. When you close the rear exit, the conditions in the front of the aircraft actually become worse, become more life-threatening. The conditions in the middle of the aircraft are pretty much the same, hasn't had much of an effect. But closing that exit actually makes the conditions in the front of the aircraft less survivable. And the other scenarios, it doesn't change the fire conditions in the aircraft very much. There's some changes, but not a lot. And this gives you an idea of the fire simulations. We're looking at a longitudinal section through the aircraft. This is the base case, this is what actually happened. This is with the S3 exit and R2 exit closed. And you can see that there are some differences here between these two cases. This is another scenario that we ran in addition, which is quite interesting because this is actually, if we close that front exit completely, the R2 exit, it's counterintuitive. You close that front exit, you actually get much more survivable conditions. And I'll explain that at the end if I have time. But I want to concentrate on the actual fire cases. Now these are the interesting results. These are the number of fatalities for the different scenarios. So in the base case, we predict 55.3 fatalities. In reality, there was 55. When we opened the R1 exit 10 seconds earlier, the number of fatalities dropped by 33%. So if the guys on board the aircraft could have got that right overwing exit open on time, you would have saved 37 lives, just simply by getting that exit open quicker. The fatality rate would have dropped by 33%. If the guy sitting at the overwing exit could have got his exit opened earlier, you would have saved 43 lives. Sorry, the number of fatalities would have been 43, a reduction of 22% in the number of fatalities. And the interesting one here is if the R2 exit, the one at the end, if that was actually closed, if the cabin attendant didn't open that, just like what the press castigated this poor dead woman for opening this exit, if she didn't open that, the death toll would have increased by 17%. Actually, more people would have died. And that's because by opening the rear exit, with the front exit open as well, with the wind blowing in the direction it was blowing, it was like having a chimney effect inside the fuselage, and it was blowing out the toxic products, the heat and the toxic products. So it made the front of the aircraft more survivable. And the best result here is that if all the exits opened on time for this particular fire, if all the exits opened when they should have, the death toll would have dropped to 4.2 people on average, an improvement of 92%. That's a huge significance. This fatal fire, which actually changed international regulations in aviation, had the exits been opened when they should have been opened, people still would have died, we predict, but only a fraction of what actually happened. The other thing that's interesting in terms of the results, even when you have both these exits open, the aisle cannot provide a flow rate great enough to keep both exits open. So when you have both exits open, you don't get the full advantage of having both exits open because the aisle can't feed the passengers in quickly enough to support both exits. So it's a fundamental flaw in the design of these aircraft. Not just this aircraft, but all aircraft. Showing you here the evacuation simulation. This is the base case, and the exits are going to be opening in the same period of time as actually having the real incident. The fire has started and the smoke is spreading forward, and here we have the final scenario where we have all the exits opening in the correct time. You can see most of the people have got out, the smoke is spreading, the toxic gases are spreading. There are still people just getting through here. This is a pretty bad environment. There's loads still in here. That person just gets out. And here you can see the fatalities, the 4 fatalities. And here you can see the 55 fatalities piled up in the aisles. Okay, so it's a stark demonstration of what can happen if you don't get the exits open in time. So to conclude this then, a couple of slides. The Smart Fire and Air Exodus simulation tools have been used in a forensic analysis of the 1985 Manchester 737 fire and evacuation. The accident reconstruction derived several key unknown parameters that we could use in the model, and we then explored what-if factors to explore the impact of the exit opening time on the fire and evacuation. In the Manchester accident, exit R1 was opened 60 seconds later than expected due to a door malfunction, and the question was, could the loss of life have been significantly reduced if the R1 exit had opened earlier? And what we found is that without this delay, the loss of life would have been decreased by 33%, or 19 souls would have been saved. The narrow aisle aperture severely restricts the flow into 2 exits, and you don't achieve the full benefit of having those two exits open, but it's still better than having only one exit open. In the accident, the right overwing exit, passenger-operated exit, was opened 33 seconds later than it should have been, and the question was, did the delay in opening the right overwing exit impact survivability? Well, the answer to that is, without this delay, the loss of life would have been decreased by 22%, or 12 souls would have been saved. Airlines, and a point here is that airlines should rigidly enforce the regulations associated with passengers seated by Type 3 exits, and should perhaps even go further and improve the training of passengers seated by these exits. The quick opening of the exits is essential in aircraft evacuation involving fire. If the exits were opened within the certified time, the time that's demonstrated in the certification trials, the loss of life would have been decreased by 92%, and so 51 lives would have been saved. Exit R2 was opened before the aircraft completely stopped, but not used in the evacuation due to the heavy smoke accumulating in that area. Did the opening of the R2 exit contribute to the high loss of life? Well, the answer to that is no, it didn't. This action probably saved lives, and we predict something like 9 more fatalities would have resulted if the R2 exit had not been opened. Thank you very much.